Okay, last sort of getting halfway through the lecture now. I hope you're bearing with us. We're going to talk next about objects subject to gravity only. So, in other words, free fall. Not a whole lot to discuss on this slide, but the point we want to make is that if gravity is the only force on an object, and we ignore things like air resistance, lift, if you're talking about airplanes, those sorts of things, and changes in altitude. Altitude are not enough to cause changes in g, then we will have constant acceleration. You'll learn next semester that g is actually a function of the distance from the center of the Earth. So if you have big changes in elevation or altitude, g actually varies even quite a bit as you go up towards outer space. And of course, ignoring air resistance, that means the only force on an object that's falling would be gravity, and gravity, very good approximation to be constant. Here are our values right here, 32.2 feet per second squared. Again, that's an approximation based on your altitude, but we'll use that number unless told differently. The equivalent of that is 9.81 meters per second squared for SI. So I know I've said it, but this only applies when you're freely falling. Okay, we need to remember that. One of my pet peeves is people who use an acceleration of g just arbitrarily. Whether you're going sideways, up, down, other forces involved, the only time this applies, the only time your acceleration is equal to g is if you're freely falling and you ignore air resistance and ignore small changes, or you have small changes in altitude. So one more time, only during free fall. Okay, if we were in lecture, I would show a video perhaps from the Hitchhiker's Guide to the Galaxy. You can YouTube that, maybe take a break now, and YouTube the video of the whale and the petunia from Hitchhiker's Guide in the Galaxy. Sort of an interesting conversation as they fall through the air. Alright, so let's crush a Mini Cooper. Give a window here. So this will be a pretty simple example of free fall. We want to crush a Mini Cooper. Don't bother asking why. We can make up lots of reasons. A crane lifts a 10-ton weight 50 feet above the Mini Cooper. Waits until the driver looks up, drops the weight. What's the speed of the weight when it hits the Mini? How long did the driver have to escape? So one of our goofy word problems, we want to filter through all the words and figure out what we're given and how to solve the unknown. It's going to turn out to be a pretty easy problem. So we'll write the weight since we're given 10 tons. 50 feet, let's draw a little picture. Alright, so I'll draw my picture of the Mini Cooper right there. We're 50 feet above it with the weight. So if I set my datum here going positive up, my final position is going to be when it hits the Mini Cooper, so that'll be 0, and my initial position would be 50 feet. Okay. There's one more word in here. When we say drops, that implies the initial. Okay, come on, pen. You can do it. Something's paused here. Alright. That implies the initial velocity is 0. That comes from right there. Okay. We want to find the final velocity. we want to also find the time. Alright, so we'll work each of these parts of the problem one at a time. We'll pick the V2 first. Alright, so we got our equations down here at the bottom. If we want to find V2, we don't know delta t, but we know that other stuff. We need one more thing. What's our acceleration? Well, that's the whole point of this slide. Our acceleration is g, but it actually is minus g. Okay? So we'll use g sort of generically as the magnitude of the acceleration, and then based on the problem we're going to factor in whether it's positive or negative. Since we've chosen positive is up, g is always towards the center of the earth. So I'm going to scroll back up and write that on this slide. G is always, we'll highlight always, toward the earth, towards the center of the earth. Okay. We can choose our coordinate system either way. So we could choose down as positive, g would be positive. Usually we'll use g or positive upwards, and g will be negative, or the acceleration will be negative. G is just a magnitude. So let's see, we're working in feet, so in this case it's going to be minus 32.2 feet per second squared. Alright, so if we want to find V2 without factoring in delta t, we can use this equation right here. Okay, we know S1, we know S2, we know V1, and we know our acceleration. Alright, I'm going to go ahead and do this algebraically. You don't have to. You can plug in numbers, use the solver, solve it algebraic, whatever. But I'm just going to rewrite this as, I'll read it first here, S2 equals S1 plus V2 squared minus V1 squared over 2A. Alright, I'm going to solve for V2. Okay. And I'll skip the intermediate steps, but it looks like it's going to be 2 times A times S2 minus S1 plus V1 squared. Okay, again, you don't have to work it this way. We'll just do this to demonstrate different ways of doing things. So then I can plug in my numbers. 2. Here's where you got to be careful. Minus 32.2 feet per second squared. S2 minus S1 is 50 feet plus V1, 0 squared. Okay, remember our units. I didn't write them in here, but they need to be consistent, so I'll sort of write them below. This is feet per second squared, and this is feet. Alright, so I'm solving for V2, so I've got feet times feet over seconds squared, and it's all under square root sign, so that will actually give me the velocity in feet per second. So V2, I'll use my trick over here again. Oh, let's just use the use the calculator since we got it handy here. Except I can't quite get to everything. So this one's pretty simple. I'll get out of the solver and let's see, we can see everything there. So it looks like if I do square root 2, oops, I see a problem. Minus 32.2, I'll go ahead with it. 2 times minus, can't do it quite right here. I'm going to use the keyboard, times minus 32.2, I think you can see the problem, times 50. I got a little ahead of myself, but that's good. Alright. Non-real answer. Take square root of a negative number. Oops, is that what I wanted to do? Where's recall at? Alright, so I just hit second enter to recall the question. Let me go back over and explain why that is. That is because this has S2 minus S1. We said S2 was 0. S1 was 50. Okay, so this is a really common mistake. So I got skipped a little bit of a step here, and I should have written, if I can fit it in here, let's just try and scratch this out and rewrite it correctly. 0 minus 50 plus 0 squared. Okay, so on my calculator that should be negative. Okay, 212.3 feet per second. And I don't have a good feel for feet per second, but just for reference, we'll take that and divide it or multiply. Let's see, we're going feet per second, so we'll multiply by 3,600 seconds per hour to get hours on the bottom, and divide by 5280, about 145 miles an hour. All right, that ought to do that Mini Cooper in. Okay, hopefully you're working along and have a question right now on why that number might not make sense. I had the luxury of pausing and going back and double checking things and noticed my error. Getting in a hurry with the calculator, so always double check your answers. I had right here, point to it here, 2 times minus 32.2 times a minus 50. Up here I have 28 times minus 30.2 times minus 50. Okay, so I just did not take my time on the calculator. So let's fix that really quick. Second, come on. Enter, second, enter to get back to that calculation. And go over and delete my 8. And get a lot better answer. 56.7. And then times 3,600. By 5280 to get miles per hour. Alright, so let's scratch out those wrong numbers. Lost my calculator. Come back here. Let's see, 56.7 and 38.7. 7 and 38.7. I believe those are the right numbers. Feet per second, miles per hour. And I still haven't done the second part of the problem. How long did he have to escape? So we need to find our delta t. I don't really want to have to, well, actually this one right here looks like a real easy equation. Okay, I know now v1 and v2. I know the distance it traveled. I can calculate the delta time real easily. I could use this one as well. Okay, and that would give me the same answer. This one's pretty easy. The second one, the middle one here, is pretty easy when our initial velocity is 0. So either will work. Let's just sketch them out real quick. Remember S2 minus S1. I'll write it out here. S2 equals S1 plus V1 delta T plus 1/2 AT squared. Alright, so we had 0, 50, 0, I'll write the T there, 1/2 minus 32.2 t squared. So t is going to be square root of 2 times minus 50 over minus 32.2. And I won't take the time to calculate that value out. I'm going to cheat and look it up here. Looks like I'll get on the right problem here. 1.76 seconds. Again, several different ways of doing it. We could actually also use V2 equals V1 plus AT and use the number we calculated from above, 56.7 equals 0. Let's see. Let's double check. I'm stumbling here. Alright, this will make another good point here. Alright, we calculated V from this equation right here, which involved taking a square root. Okay, and so that actually gives us two answers right here, plus or minus. So the question asked for speed, so giving a magnitude of 56.7 feet per second is fine. If it had asked for velocity, we would have actually chosen the negative one because we chose positive is up, and so the velocity when it hits is minus 56.7. That's important because we have to use the vector value here. Alright, so this should be minus 56.7 minus 32.2 times t. Okay, and t would come out to be the same thing, 1.76 seconds. So important point there, you do have to be careful with the signs. Obviously I got in a hurry and almost forgot them, but I noticed they don't work out, and they usually don't work out for a reason. Alright, 18 minutes on that one. Too long, but I don't have time to redo it.